Okay, let's start off today by reviewing a little bit about yesterday. We talked about properties of acids and bases. Who can tell me a property of an acid? Okay. It has a sour, acids have sour taste, but remember, we stated we should never taste an acid to determine, hey, is this an acid or not? I'm going to try it to see if it's sour. Not a good idea, but nonetheless, you have had acids before because you've had citrus fruit drinks, okay? What was another property? Acid-base indicators, okay? That goes for both of those. The acid-base indicators will change colors. We'll do a lab coming up maybe next week on one of the 2-hour delay days. I think we'll have enough time to do some acid-base indicator labs. So I might plan one of those because we got 2 delays coming up, okay? What else? What was that, Ethan? Conduct electricity. Do bases conduct electricity? Yeah, both of them do. Okay, what's something about a base? Bitter, right? Once again, we should never taste that they are bitter. What about when they get wet? They are slippery when wet. Slippery when wet. Arrhenius, up there on the board. Arrhenius, we talked about Cervantes Arrhenius and his ideas. What were his ideas about acids? What were Arrhenius' idea about acids? When they dissociate, what happens? They form hydrogen ions when they dissociate. Okay? Also, Arrhenius said about bases, when they dissociate, they form what? Hydroxide ions. Okay? We will build on that later on when we start talking about Bronston and Lowry. I think that'll be tomorrow. Okay, but we'll build on this. This is just an early introductory definition of what Arrhenius felt that acids and bases were. This is some new stuff, folks. Today, our goals are to talk about strength of acids and bases, and we're also going to do some calculations of acid dissociation constants, the K sub A. So our goal today is to understand a little bit more about the strength of acids and bases, whether they're strong acids, weak acids, and how to calculate the acid dissociation constant. Now remember, I told you yesterday that sometimes we just refer to these as an aqueous solution, and we take the water out of that. So, when we do so, we have, when we do so, we have equations that don't have the hydronium ion, the H3O plus 1 ion, and just the hydrogen ion. And they look something like that. Okay? So these are just 2 other ways in which we can write these to take out that water. And if we take out that water, the H3O plus is just an H plus. So you'll see these written in both ways. So just make yourself aware. But the important thing about this slide is strength is equal to dissociation. The stronger the acid, the more it dissociates into the ions. So if you look, here is hydrochloric acid, HCl. HCl, if you look on the pH scale, is a very strong acid. Well, when we look at the amount of dissociation, almost 100% of that acid dissociates into the H plus ion and the Cl ion if it is in water. If that is dissolved in water, almost 100% of that acid dissociates into the ions. That makes it a very strong acid. On the other hand, if you look at C2H3O2, that is acetic acid. Acetic acid only dissociates at about 1%. So close to 99% of that acid stays as HC2H3O2. And only 1% is in the H plus and the C2H3O2 minus. So it has very little dissociation. That makes it a weak acid. So the more the acid dissociates, the stronger it will be. The less it dissociates, the weaker that particular acid will be. So, up at the top of this slide, it's very important to remember strength equals dissociation. Strength equals dissociation. Now, if you look, I just put this in here. Acid strength increases. You can see right here. Acid strength increases. So right here's water, and you can look, there's ions, but here are some of the common acids based on strength-wise. You know, we just said acetic acid is pretty weak. Okay, there's acetic acid. Here's carbonic acid. Okay, and you look up here, some of the higher ones. Nitric acid, sulfuric acid, hydrochloric acid. Those three, all of them almost dissociate 100%. Okay, so those just showing you what some strong acids are and some weak acids are. When a base completely dissociates in water to yield hydroxide ions, the solution is referred to as an alkaline, a strong base. Where do you think you hear that word, the alkaline? Huh? Well, yeah, it's on. You know, we talk about alkaline. I'm talking about our common life stuff, huh? Batteries, yeah, alkaline batteries. So, you know, when bases completely dissociate, same thing. They're strong. They're strong. So dissociation equals strength with bases too. And if we happen to have a strong base, we call that an alkaline. An alkaline. I told you we were going to do some dissociation constants today. So let's get this down in our notes first of all. When we're talking about the acid dissociation constant, the K sub A, that's how you're going to see it, acid dissociation constant, K sub A, that's also known as an ionization constant. What Ka is it's the ratio of the concentration of the dissociated form of the acid to the undissociated form. So in this particular case, on top, right here, those are the dissociated forms. And the brackets mean the concentration. Now, we've talked about concentrations. How do we typically classify concentrations in chemistry? Which is what? You're right, moles per liter, molarity. So those concentrations will be in molarity. So the concentration of the hydrogen ion, right here. The concentration of the acetate ion, right there. And down on the bottom here, what I'm circling in red, that is the concentration of the undissociated form of the acid. Now, we talked about acetic acid just a while ago. The slide before this one. Is acetic acid a strong acid or a weak acid? A weak acid, correct? We said that approximately 1% associates into the ions, right? So what's going to be higher, the blue or the red? The red's going to be a lot higher because 99% of that is undissociated, right? Only 1%, based on that percentage, 99% is here and only 1% is here, right? Making that a very weak acid. So if that is the case, that number is it getting closer to 0 or further from 0? If I take 1 divided by 99, it's pretty close to 0, isn't it? Okay? Now what if I would flop that? Let's say we had hydrochloric acid. And hydrochloric acid is the other way. Hydrochloric acid had 99% dissociated and let's say 1% not dissociated. Is that going to be a bigger number? Yeah, right? So that's what we're looking at with Ka. Okay? Bigger numbers, the bigger values of Ka are going to be the stronger acids. The lower values of Ka will be the weaker ones. Garrett? Why they dissociate? Okay, just going back. Let's go back a couple of slides here. Okay, here, like this. This means, this percentage over here means that if we put this in water, almost 100% will be ions there, and this will be, almost close to 0. We'll put it at 1 just so we have something. 1%. So if you would have, we talked about conducting electricity that those ions do. That light bulb would light up really, really big because almost all of them were these specific ions. Okay? You're not going to find much of just the original HCl. Okay? And you're going to see this here in a bit when we talk about concentrations and we do the actual, put the numbers in there. Okay? I think you'll see it a little bit better. But that's what it is. It's just saying dissociation, breaking into the ions. Now this one right here, let's look at this one. We talked about 1%. That means that 1% would be the ions. And over here, that would be close to 99%. So it does not ionize. Okay, it does not ionize. That makes it weak. So let me show you here. I think, get back to my Ka. Everybody's got that written down, right? Yeah, Kyle. Don't think about it. You're thinking about like what we just did, the Kc, equilibrium constant. Okay? Don't think of it like that. Think of it as the top's going to be the dissociated. Okay? So the top's going to be the ions and the bottom's going to be the acid. Okay? Don't think of it as products reactants. Here's what I just told you there. Here's what I just told you, was trying to get across to you, that the bigger the Ka means that there's more dissociation. More dissociation means that it's stronger. The smaller the Ka, the lower the dissociation, the weaker the acid. So go ahead and get that. And when we talk about these folks, when we talk about Kas, you're going to see these Ka values are very, very small. Okay? Very, very small. We're talking into the 10 to the thirds are some of the stronger ones. The weaker ones are, 10 to the negative third. Okay? Some of the weaker ones are going to be into the 10 to the eighths. And so when I switch to this next slide here, and we look at some Ka values, okay? Right here is acetic acid. Okay, Ka value for acetic acid, 1.8 times 10 to the negative 5. Okay, so there's a lot of zeros. That's like 0.00018. So that's very, very, very low. Look at these ones over here. Okay, carbonic acid, 10 to the negative 7. Okay. Now here they just say Ka large, large, large. Okay? So when looking at these values, what you need to know if you're given Ka values like this, okay, is if you look at this, can you tell me? Okay, look at the Ka of acetic acid. Here it is. Right? Now, which is stronger? Which is a stronger acid? Acetic acid or phosphoric acid? Phosphoric acid is, because its Ka value is bigger. Okay? Which is stronger? Which is stronger? Hypochlorous acid, right here, or acetic? Acetic. So you need to be able to look at those Ka values and say, okay, which one's bigger? The bigger one is the stronger one. The bigger one is the stronger one. Now, we talked about diprotic and triprotic acids yesterday, and it was all dealing with how many hydrogens were with the anion, in this case, the phosphate ion. So go ahead and write this down here, and then we'll discuss these diprotic acids and triprotic acids. Now we look at these values here, okay? Now up here it says the acid dissociates one hydrogen at a time. What does that mean? Well, if you look at this, here's how the dissociation occurs. We take one hydrogen off at a time. So if you look, if I take off one hydrogen from H3PO4, I get H2PO4, but that has a minus charge. So this is taking off one hydrogen. The Ka, and look, the Ka1, the acid dissociation of the first hydrogen, is 7.5 times 10 to the negative 3. That's pretty high, isn't it, in terms of a Ka? Here is the second acid dissociation. So we've taken off a second hydrogen to give us HPO4 minus 2. Look at that Ka. Look at this Ka compared to that one. It's very small, isn't it? How would you relate this one compared to the first one? Very, very small. So what I'm trying to get at is that most of the dissociation of the acid occurs right here, the Ka1. When we're talking about significant figures, when we're talking about sig figs, do you think that this and this would even be noticeable? What do you think? When we're talking about sig figs, would the Ka2 and Ka3, would you even notice it? No. So when we're discussing the dissociation of diprotic and triprotic acids, we're only talking about the Ka of the first hydrogen ion coming off. Okay? So typically we don't even worry about these two. And why did I tell you? Why don't we worry about them? Because they're too small. They're too tiny, where they're going to end up not even mattering to us when we sig fig our answers. Okay? So that's why we consider the acid dissociation right here of the first one when we deal with that. Now, when we talk about a monoprotic acid, we only have one hydrogen, right? So it's only going to have one. But when we deal with the diprotics and the triprotics, we're only dealing with the Ka of 1, because that's the value that we feel the sig figs is going to be best with our data range. Here is the base dissociation constant. Okay? The base dissociation constant. We're not going to work a whole lot with the Kb. I just wanted you to see one of those and to recognize that it's the same thing. It's the dissociation form. The ions are on the top here. The ions are on the top here, and the undissociated form of the base is on the bottom here. Okay? So just be aware that once again we have a base dissociation also. But when we do the calculations, we are going to use the acid dissociation constant typically, and we're not even going to, I'm not even going to give you examples of the base dissociation constant. So we'll just deal here with the acid. Now the final thing I wanted to do today is I wanted to show you an actual example of an acid dissociation constant. So I'll give you a second here. Go ahead and copy that down, and then we're going to talk about how to calculate the acid dissociation constant, the Ka. Our question here states a 0.100 molar solution of acetic acid is only partially ionized. Using a measure of the pH, the hydrogen ion concentration is calculated as 1.34 times 10 to the minus 3 m molar. What is the acid dissociation constant of the acid? Now, I have written the equation of this dissociation up here. Here is acetic acid. It breaks down into hydrogen ions and acetate ions. Now, what is the ratio here of hydrogen ions to acetate ions? What would you tell me that ratio is? If I have one of these, how many of these do I have? One. So that is a 1-to-1 ratio, right? So if I have this many hydrogen ions, how many of this am I going to have? The same amount, right? The same amount. So when I'm talking about the acid dissociation constant, I said that the Ka was equal to the hydrogen ion concentration times the acetate ion concentration all over what? What was on the bottom? The acid, right? The undissociated form. Now, all we need to do is substitute values in. What is my H plus? What is my H plus? Right here. It tells me my hydrogen ion concentration was 1.34 times 10 to the minus 3. What then is my acetate ion concentration? The same, right? Because that is a 1-to-1 ratio. The hydrogen ion and the acetate ion, correct? Now, here's where we work with the acid. How much acid did they tell me that we had? 0.1. We're going to use that value down here as the value of my acetate, my acetate ion. So when I do my math, I multiply, remember, multiply, I had a lot of people adding these before, multiply 1.34 times 10 to the negative 3 times 1.34 times 10 to the negative 3. And divide that by 0.1, and I come up with a value of Ka is equal to 1 point, how many sig figs? 3 sig figs, 1.80 times 10 to the negative 5 for my Ka. So now I could use that value to compare it with something to say, hey, is that a strong acid? Is that a weak acid? Okay, we know where acetic acid comes into the line. It's a pretty weak one, right? Okay, so if I would look at that 10 to the minus fifth, this is pretty close to the value that they gave on the one slide, right? Okay, so I would say that that's probably a weaker Ka than some of the more strong ones, all right? But nonetheless, that is a Ka calculation. We will do more of these tomorrow. I might adjust our schedule a little bit because we're at least going to work 3 of these problems tomorrow. So I might adjust our schedule a little bit. I don't know how much we're going to talk about pH. Okay? Now, one thing, if you look up here, it says using a measure of pH. Okay, so if we measure the pH, we can determine the hydrogen ion concentrations and vice versa. If we measure the hydrogen ion concentration, we can convert that into a pH. And you will learn that either partially tomorrow when we start talking about that or on Monday. Okay?